Uh, Good evening, all, and welcome to one more session, the fourth session of 2024 of Institute of Naval Architects. Today's session will be presented by Dr. Abhilash of IIT Madras. Our chief guest for the day is Captain KP Jayakumar, and the session chair is Mr. R. Srinivas. Today's talk will be on the topic COLREGS compliant collision avoidance for ships using artificial potential fields. For this webinar, it's my pleasure to introduce the session chair for today, Mr. Srinivas. Mr. Srinivas is the Vice President and Senior Principal Surveyor at Indian Institute of Shipping. He specializes in controls and automation systems, system integration, maritime cyber risk management, and failure mode effect analysis. Mr. Srinivas has 40 years of maritime experience. During his 13-year tenure in shipbuilding, he was in charge of installation, commissioning, and testing of electrical, control, automation, navigation, and communication system on board. He has 12 years experience in ship designs and was involved in the preparation of class drawings, production drawings, and headed various consultancy projects for shipyards, NAVOT, ONGC, and ports in automation, networking, and TMS. He is with IRS for more than 15 years and is heading Electrical and Control Systems Department and is involved in new technology projects. He was the chair ISCS Cyber Systems Panel and also chair for ISCS Joint Industry Working Group on Cyber Systems from October 22 to April 2024. He is presently IRS member for ISCS Safe Digital Transformation Panel. With this brief introduction of the session chair, I would hand over the session to the session chair, sir. Mr. Srinivas.
Thank you. Thank you very much for the kind introduction. And I consider it a privilege to host the chair today and much more privilege to introduce the chief guest, Captain KP Jayakumar, ex-Nautical Advisor-Cum-Addl DG Nautical, DG Shipping. I think that itself is a big presentation, introduction for him, and the industry knows him by the word and the name. So I don't think I need to introduce much more than that. Welcome, sir. Now I will take a couple of minutes. The main speaker today is Dr. Abhilash Somayajula. He has been an assistant professor in the Department of Ocean Engineering in IIT Madras since 2019. He is the Director of Marine Automation, Autonomous Vehicles Laboratory at IIT Madras. He also founded the Center of Marine Automation Systems that is now a part of Center of Excellence for Maritime Experiments at IIT Madras. He has a collaboration with several foreign universities, including IST Portugal, National University of Singapore, MIT, and Texas A&M University. Before joining IIT Madras, he worked as a research assistant professor at Texas A&M University. He graduated with a bachelor's and master's in ocean engineering and naval architecture from IIT Capt. Dr. Abhilash earned his PhD in ocean engineering from Texas A&M University. He also has a micro master's in robotics from University of Pennsylvania. His research interests include hydrodynamics, fluid structure interactions, application of artificial intelligence for marine systems, and marine automation models. That was a great CV to read out. I am privileged to introduce and request Dr. Abhilash Sharma to go ahead and present the topic. Over to you, Dr. Abhilash.
Thank you, Mr. Srinivas. Is my screen visible?
Yes, sir. We can see your screen.
Okay. All right. Good evening, everyone. So thank you for that great introduction, Mr. Srinivas. So I'm Abhilash Somayajula from IIT Madras. And today's topic will be on COLREG compliant collision avoidance for ships using artificial potential fields. So today's agenda will be I'll cover a little bit about what we do in the Marine Autonomous Vehicles Laboratory at IIT Madras, and then head into how this topic really fits in the story together with our lab. And following that, we'll talk a little bit about the modeling, the obstacle avoidance, collision avoidance, statistical analysis, and reach some conclusions from it and see how this can be useful in the future. So Marine Autonomous Vehicles Laboratory was set up after I came and joined IIT Madras in 2019, and we do a lot of interdisciplinary and multidisciplinary researches. And we look at the intersection of three primary areas: hydrodynamics, artificial intelligence, and control theory. So in hydrodynamics, we are interested in fluid structure interaction, and we have developed our own program which parallels VAMIT or Aqua or any of these commercially available softwares. But our intention was to kind of go beyond it and be able to simulate certain phenomena which are otherwise not simulatable with commercial softwares. So our software is actually available for free for everyone to use. It's nicknamed Hydra for hydrodynamic response analysis and can be accessed from the URL which you see here. So the idea behind this hydrodynamics program is to be able to calculate nonlinear phenomenon and calculate nonlinear pressures acting on a hull in the presence of nonlinear waves. And the idea is to see and simulate responses which otherwise cannot be done using linear theory. So here I show an example where you see a vessel in a wave basin which is experiencing head-on waves. So a ship which is being symmetric on port and starboard side, when it experiences head-on waves, one doesn't expect that it should roll very much. But if the conditions are just right, you can actually see that a considerable amount of roll comes into the picture. And this sort of a phenomenon is a nonlinear phenomenon which we like to try to simulate with our simulation tools and validate them with experiments. So the idea is to understand stability of these vessels and how can we design vessels effectively so that they don't experience this in their design life. Something else which is of interest to us in the MAV laboratory or Marine Autonomous Vehicles Lab is artificial intelligence for ship collision avoidance. Particularly what you see here in the video is a simulator example where we are simulating about 10 ships, and we are trying to see whether all of the ships can interact with each other and try to learn the policy how to get to their goal while avoiding collision with each other. Something else of interest is system identification, which means from a free-running experimental data, can we identify a good hydrodynamic model for the vessel? And how best does it represent when we identify things from data which is a little biased? So these are some of the research topics which we do handle. Something recently we have been looking at is also on physics-informed neural networks. So particularly with respect to ship hydrodynamics, the maneuvering coefficients are quite a challenge to predict. And we have some work going on as to using pins in order to try to identify these approaches for them. The third area for us is on control systems, where we look at guidance, navigation, and control methodologies. And we try to look at it from a traditional perspective in addition to the artificial intelligence perspective. So when we use the artificial intelligence-based methods, one of the downsides is interpretability. So whatever we are getting out of it may not be very interpretable. And it's quite the challenge to actually understand how the decisions are being made by deep learning models or machine learning models. Whereas control theory gives us a traditional approach to do this, and we do look at collision avoidance methodologies, which leverage more on these traditional approaches. And today's talk really is stemming from that part of our experience in the lab, where we are looking at a COLREGS compliant collision avoidance system for using artificial potential fields. All right, so with that introduction, I'll jump into the topic. So we know that when we look at the number of different ship accidents which happen across every year, and when a statistics is calculated as to what is the leading cause of this, it usually is associated with a human error, whether it be in terms of an action which was erroneously taken by a human, or an action which was not taken by a human which resulted in the accident happening. So this has kind of brought up the idea of, if we automate our ships, we can take the human factor to a large extent out of it. And that is the major drive which happens for automation of ships or autonomous ships as we see them. So some of the challenges with autonomous ships is to be able to do path following, collision avoidance, and obstacle avoidance correctly. So I make a distinction here that obstacles avoidance, I mean that the obstacles are static in nature. Whereas when I say collision avoidance, I'm talking about dynamic obstacles which have their own kinematics or dynamics, and they're moving within the environment as the own vessel is also moving. So in our group, the major interest has been to see whether we can go in the direction of these three items, the path following, obstacle, and collision avoidance. And I'll cover that from the perspective of how we can leverage artificial potential fields for that idea. A note here is that we are planning to do this for traditional ships. So the pictures on the right, you can see on the top is a traditional container ship, which we see out there. And on the bottom, we see a catamaran defense vehicle. So both of them are ships, but here our focus will be more on mono-hull ships with single screw propellers, which really represent a under-actuated vessel. When I say an under-actuated vessel, I mean that I'm trying to control 3 degrees of freedom, which means forward and sideways lateral motion, which are the surge and the sway motions of a ship, and the yaw motions of a ship. So all of these motions happen in the horizontal plane. And we have only two actuators to do this. So we are trying to control 3 degrees of freedom, but we have only two actuators, the actuators being the propeller and the rudder. So this is what is called as an under-actuated system. And particularly a ship cannot sway sideways suddenly. So there is no way for a ship to sway suddenly sideways. So this poses a control problem and a challenge in terms of both path following and collision avoidance. And we'll see how we deal with those ideas. Catamarans, on the other hand, can turn in place. So that ability is not there for ships. So we really wanted to focus on systems which are highly underactuated and see how we can develop algorithms for doing collision avoidance for them. Okay, when we talk about obstacle and collision avoidance, there are different methods which have been explored in the past. And some of these are rule-based approaches where there simply is a rule set which you would like to follow. Sometimes you would like to do an optimization like a model predictive control or MPC. Here we actually try to look into the future. We have a model of our craft and we try to see into the future a little bit as to what happens when we take different control strategies. And the best one is what is picked up, and that is used for that time step. And this whole process repeats at the next time step. As you can already imagine, this part is a little bit more computationally expensive. Then you do have hybrid methods which try to kind of leverage a little bit on optimization methods, but also try to use a little bit of black box modeling. And that's where RRT COLREGS comes into the picture, is a good example of this sort of a method, where you're trying to leverage some way halfway between optimization methods, which are model-based, versus a little bit on the data-based or information-based. Finally, at the deep end of the spectrum, we have the deep reinforcement learning methods or RL methods. And there have been a bunch of variety of methods which have come out over the years, including deep Q networks or proximal policy algorithms or DDPG algorithms, so on and so forth. And each of them have their own advantages and disadvantages. One of the challenges with deep learning, deep reinforcement learning methods is the interpretability part, which means when the policy is learned as to what decisions to take, it's not always clear as to how those decisions are being taken. Because it's learning a lot from the data, interpretability becomes a big challenge. Finally, we have the reactive methods, which have been traditional approaches. And in these two approaches, we'll have two main ones come up, which are artificial potential fields and velocity obstacles. So we'll talk a little bit about both of them, and we'll try to compare both these methods in this talk. So the main reason to choose artificial potential fields is that it is really fast and it is really easy to implement. And the idea is that we can try to see if we can modify some of these artificial potential fields to incorporate COLREGS as well, which are the rules of the water navigation ways, which are specified by the IMO. Okay, so the first thing before we start off with any of these problems is to model this issue. And we do build a simulation model of our own. The idea here is to be able to simulate the dynamics of the vessel with different controllers and see how the two perform so that you can compare and contrast them. We are going to be using in this study a standard simulation model developed by the MMG group, which is called the Maneuvering Model Group from Japan. And this consists of a simplified model where you, on the right-hand side, you have the three equations of motion, include the dynamics from mass, inertia terms, Coriolis terms, and added mass terms. And the three forces, which are representing X, Y, and N, represent the external forces acting on the vehicle. So notice here that U, V, and R are my state variables here. U stands for the surge velocity, which means the velocity of the craft in the body fixed frame towards the bow of the ship. V is the body fixed sway velocity, which means it's the lateral velocity of the ship. And the turn rate is denoted by R. The external forces X, Y, and N can further be separated out into their components. And the components would be what are the forces acting on the hull, and what are the forces coming from the rudder, and the forces coming from the propeller. Now, there is a detailed modeling which MMG group gives out as to how these terms on the right-hand side can be calculated. For the brevity of time, and also that these are very standard approaches, we'll not be going into the details of those in this talk today. So once we built this simulation environment, we wanted to validate our simulation model against experimental data. So the idea here was to compare against the MMG experiments which were performed by Yoshimura et al. And the idea was to see if we performed a turning circle trajectory, does the turning circle trajectory agree between our simulation model and the experiment? Obviously, we do see that the transient motion is definitely going to be different because some of the hydrodynamic derivatives which we feed into the model are valid only for a specific design speed. So obviously, the transient motions will not always match between different models. However, the main interest here is to see whether a turning circle diameter and things like that, fair statistics, do they have a good match? It's important to note here that you do see on the graph on the right that Yoshimura's experiment, which are the magenta colored dots, seem to have the same turning circle radius as the simulation which we have performed here. But experimental data from another source called Marin's experiments do not seem to match very well. This was a concern for us when we were looking at it because we wanted to investigate why is there the difference between them. And then we realized that Marin's experiments were conducted at a slightly different scale versus Yoshimura's experiments. So Yoshimura was conducting experiments with almost a 3-meter model with a scale ratio of about 75, whereas Marin was conducting a model scale experiment with a 7-meter model with a scale ratio of about 38. So when we try to do the fruit scaling between the model and the real deal, we are able to match the inertial forces very well and the gravity forces very well. So which means the wave forces get matched really well. But we will never be able to match the Reynolds number between the model and the prototype. And hence, when two different studies are performed at two different scales, you expect the hydrodynamic derivatives, which are a strong function of Reynolds number, to be quite different. And that's why you see that the turning circle radii will be different between the two different scales of experiments. These are known as scale effects, and we are able to see that actually happen in this case. Now, once the simulation model is built, we need to design the guidance algorithm. And the main idea of the guidance algorithm is to specify how to bring the craft to the path that we want to follow. So the picture on the right shows you that we want to follow a path, a straight line path from waypoint on the left to the waypoint on the right. So the waypoint on the left is the xk, yk point, and the waypoint on the right is the xk plus 1, yk plus 1. At any instant of time, the ship may not be exactly on the line connecting the two waypoints, and the guidance algorithm must try to ensure that the ship actually reaches this line connecting the two waypoints in a smooth manner. And that's the main reason why we use guidance algorithms. So the idea here is you drop a perpendicular from the ship's current location to the line joining the two waypoints, and the perpendicular distance between the line to the ship is what we call as cross-track error. And the guidance algorithm is trying to minimize this error to zero in a smooth manner. And that's how we come up with this expression, which you see on the right, where the psi desired, or the heading which is required of the craft, is specified as the heading between the two waypoints, which is pi p, minus some term which is depending on this error, or the perpendicular distance from the line joining the waypoints. If this error goes to zero, we can see that the heading actually agrees with the line joining the two waypoints. And I'll not go into the details of how do we actually get this tan inverse into the picture. The main idea here is that you want to specify a look ahead point, which means that at any point we are trying to see if the desired heading can be specified at a point delta distance ahead of where it is along the path. So maybe I can show my pointer here a little bit. Is my laser pointer visible on the screen?
Yes, it's visible.
Okay, all right. So we are talking about this delta distance ahead. So the idea is that at the current time, the ship is along the path at this point, X reference and Y reference, but we are trying to orient the ship a little ahead of it, which is given by this delta distance, which is called as the look ahead distance. So when the YPE is large, or the error is large, we see that the craft will be oriented, or the guidance algorithm will try to push the craft perpendicular to the path joining the waypoints. But as the craft comes closer and closer, it will smoothly try to orient the craft towards the line joining the waypoints. And that's the main idea of this guidance algorithm. You will see that there is a secondary term here, which is called YPint. This term primarily comes in to take care of the fact that if there are external disturbances like currents or winds acting on the craft, we still are able to follow the straight line effectively. And we'll not go into the math of this, but the idea of this math is to make sure that the guidance algorithm has certain good convergence properties, which are important when we design these guidance algorithms. Okay, once we have this guidance algorithm in place, which is trying to now make sure that the vehicle tracks paths between waypoints, we want to switch between one waypoint to the other as we come closer to one of those waypoints. And the switching mechanism here is described. So we have a dotted circle around each waypoint, which is of a radius called R tolerance. And this tolerance is usually specified in terms of the number of ship lengths. Is it one ship length or two ship lengths? As long as the ship enters this circle, we assume that that particular waypoint is tracked, and we can specify the next waypoint to the guidance algorithm to make sure that the vessel starts tracking the next waypoint. And you see here the implementation where we are able to track a square of about 20 ship lengths around the ship, and a switch happens every time it gets into this dotted circle. That's why when we plot the cross-track error, you'll see these jumps which are specifically looking at about 3. The magnitude of this cross-track error will be 3 ship lengths. We see that the guidance algorithm does well, and the controller is actually able to track the desired heading fairly well, and we are able to see a waypoint tracking emerge out of this architecture. So we in our lab are interested in not only in simulation models, but we are interested in seeing this on real scale ships, or at least model scale ships. So we have built in our lab a model scale of this container ship. And what you see on the video on the right is an implementation of the guidance and control algorithms that we have discussed so far. So it's able to track a 40 meters by a 40 meter square out there, which is specified by 4 waypoints. This craft is equipped with sensors. So we use the GPS and the IMU sensors on board, which allow us to actually specify and locate where the craft is at all points of time. And using that information, we are able to then ask the controller and the guidance algorithm to make sure it tracks the path that it needs to track. Okay, so once this architecture is in place, we are ready to jump into the obstacle avoidance problem. And to begin with, we'll look at obstacle avoidance, where we are dealing with static obstacles. And later we will see how this can be extended for collision avoidance, where we have dynamic obstacles. The main idea is that we specify a safe radius around the ship, and as long as an obstacle is inside the safe radius, we have to consider it as an obstacle for which we have to apply an avoidance algorithm. For obstacles which are outside of this ship length, 15 ship lengths, safe radius, we do not consider them in our guidance algorithm until they start figuring inside this radius. We also have to specify a radius of the obstacle, and in this study we have specified all obstacles to be almost the same size as the ship size, so which are really large obstacles. But obviously you can even inflate the radius around the obstacles to have a higher margin of error, and that just is a much easier way to incorporate safety into the picture. So let's take a step back and summarize as to what all has happened so far. So on the right-hand side here, we have the plant or the dynamics, which is the actual craft if we are doing an experiment, or it is the simulated dynamics, which if we are using the MMG model. Now, we measure estimates of the state using sensors from this craft if it's an experiment. Whereas if it's a simulation, I exactly know all the states of the vehicle, which include the velocities in surge, sway, and yaw, and the positions and orientation of the vehicle. Once these are available to us, we can figure out which of the obstacles are present inside the safe radius around the ship's location. And if there are obstacles present inside the safe radius, we choose a reactive guidance mechanism. If not, we choose the line of sight guidance mechanism that we discussed previously. So if there is no obstacle within the safe radius, we use the same principle as we saw in the video previously, and that will give us a desired heading from the guidance law that will be tracked by the controller using a rudder command, and then the plant executes and makes sure that the psi desired is achieved. But when there is an obstacle inside the safe radius, we must be a little bit more careful, and we have to choose a reactive guidance algorithm so that we can try to be, we can avoid the collision with the obstacles and figure out a desired heading appropriately. So we'll now focus our efforts on this box right here as to what are the different guidance, reactive guidance methods, and we'll specifically focus on artificial potential fields based navigation. Okay, the artificial potential fields is quite a old way of doing the things, and this kind of stemmed from the idea of traditional robotics, where they were using robotic manipulators or robotic arms, and they wanted to figure out what is an efficient way to reach the goal orientation or a goal pose from a given starting location. And the best way to figure out, and fast and cheap way to figure out, was what was artificial potential fields. The idea here is that you presume that the goal and the obstacles have their own potentials around them, and the ship is operating in a field of these potentials. So think of them as electrostatic charges, and as if you are experiencing forces on them. Or you can even think of them as large celestial bodies which are exhibiting gravitational forces on you. So it's the same principle which is being applied here, where we have an attractive potential towards the goal, which means all the potential gradients will try to pull us towards the goal. Sorry about that. Yeah. And you can see that the arrows here show the direction of the vector field. So all the directions of the gradient of this potential towards the goal try to bring the vehicle closer to the goal. Whereas when we have obstacles, we are trying to have a repulsive potential here, which is trying to repel the vehicle away from the obstacles. And this is done in terms of a squared distance law. So which means the potential is proportional to 1 by square of the distance between our vessel to the obstacle. And the greater is the distance, the smaller is the potential. And the smaller is the distance, the greater is the potential, which means when I take gradients of this, the gradients are really large, close to the obstacle, but far away from the obstacle, the presence is almost nil. So we combine both these potentials, the attracting potential as well as the repulsive potential together and take a gradient of it. And that gradient tells us the desired heading angle which our ship needs to follow. Implementing this into the algorithm, we see a test case scenario on the bottom right, where an agent is tasked with going from 0, 0 to 50, 0. And I'm talking in terms of non-dimensional values in terms of ship lengths. So I'm trying to go to a distance which is at least 50 ship lengths away from my original location. And exactly at the midpoint, I have an obstacle located at 25 ship lengths away. And as the ship starts approaching and enters into this larger safe radius, a repulsive potential starts acting on it. However, you see that the goal potential is really pulling it strongly, so it takes for it quite a bit of a time until it comes really close to the obstacle before it starts to get really strongly repelled away and takes a turn before it reaches its goal eventually. If we look at what happened to the rudder angle, we see that there are very sharp rudder commands which are asking it to go from minus 35 to 35, and the rudder does get saturated in this exercise. Now, and we see that the distance between the obstacle and the agent really comes close to the threshold of 2 ship lengths, where almost a collision was imminent. But you and I know that that doesn't seem to be the most intuitive path one can take to actually avoid collision. And we'll come up with newer definitions of potentials which can actually help us do that. One of the other challenges with these existing potentials is that it depends on the distance to the goal. So if the distance to the goal is farther away, then the pull towards the goal is that much stronger. So we see that in the example shown here. So picture on the right is what we saw previously. Picture on the left is what we saw previously, and the picture on the right is a slight variant of the picture on the left, where the goal has been placed 10 ship lengths away further. And you see that once the goal is farther away, the agent is not able to escape the collision radius, and eventual collision does happen. So even though this methodology of traditional potential fields work very well for robotic arms, they don't really work well for mobile robots. So there are some differences, and we need to formulate better possible potentials which can take care of this problem better. So in this study, we looked at and investigated what are called harmonic potentials, which are kind of based on fluid flow dynamics. So the idea here is that the goal will now no longer be drawn by a quadratic potential, but by a sink potential, which means it's acting like a sink where all the water is being drawn out of it. Similarly, the obstacles will be thought of as potentials which are having vortices at them. So we'll have a flow field around the obstacles, which is described by vortex flows, while closer to the goal location, we will have a sink potential. And this sort of an approach really gives us a much smoother path, and you can see that from the picture on the right. So the green line is what we saw previously with the inverse square traditional APF, but with the modification, you see the blue line and the black line are leveraging more on the sink and the vortex potentials to achieve a much better collision avoidance proposition. If you actually compare the new APF versus the traditional APF, you see that the margin of error is much larger, and also that the rudder angle doesn't really saturate here. So it's a win and a win situation for all parties. Okay, so we have covered static obstacle avoidance, but what about dynamic collision avoidance? So we go back to the previous potential which we saw, and here you will have observed that there is the second line which is trying to control the strength of the vortex based on the relative velocity of the craft with respect to the obstacle. So we do see that if we can scale this strength of the potential for the vortex potential in terms of the velocities which the craft has relative to us, then we can effectively try to avoid even dynamic obstacles. We also include a factor F in here, where we try to encourage the agent to do a stronger vortex when a larger collision imminent, a faster collision is imminent. And when the collision is not that imminent, this factor F will traditionally go to the default value of 1. Now, we will not go too much into the details of what exactly the mathematics is going on here, but let's take a little bit of a results look so that we can try to understand. When we talk about collision avoidance, really there are some COLREG rules which we need to follow. These are rules which are set up by the International Maritime Organization. And one of the rules from there is called rule number 13, which specifies when a vessel is being overtaken, then the overtaken vessel, the vessel being overtaken should keep out of the way and should stand on. Whereas the vessel that is overtaking should try to keep out of the way of the overtaken vessel and try to not interfere with the vessel that it is trying to overtake. So the idea here is that the yellow agent which is being overtaken should not change its course, whereas the blue agent which is trying to do the overtaking action must try to find its way either from the port side or from the starboard side. So here we see the application of our APF methodology, which tries to make sure that it takes more of a starboard turn and tries to avoid collision with the slower ship. Here we see the same algorithm being applied using traditional APF, where both the agents are now kinematic, which means that both the agents have the same policy, and we are trying to see how does the two agents try to track their own goals. It's important to specify here that the blue colored star indicates the starting point, and the star along with a dotted circle represents the goal waypoint for the agent. So the blue agent is stopping here, whereas the green agent is trying to go here. And we can see that it still struggles to come up very close to the slower agent before it takes a complete U-turn and tries to avoid the slower craft. So we know that we can do better with the modified APF. So as we go and talk about the new modified APF, I also wanted to compare it against a different approach which is popular in the field. And this approach is known as velocity obstacle approach. And the idea here is that we want to consider two ships which are on a collision course, and you can actually identify a set of velocities which are not good for your own ship, or which will lead you to be on a collision course with the opposing ship. So instead of specifying when the collision is going to happen in the geographical space, this idea deals with it in the velocity space. So we specify a cone of velocities, and if our velocity lies anywhere inside this cone of velocities, then we are on a collision course with the ship. Now, this picture here was taken from the reference given below here. where they describe this phenomenon in detail. The idea was to see how does APF, which we have proposed in the study, do any better than other approaches, including the velocity obstacle approach. So when we implement the velocity obstacle approach, you actually see that it prefers to go more on straight lines rather than curved paths. And you can see that it tries to push both the agents into a velocity field where they are diverging from each other. However, in the overtaking scenario, we will observe here that there is a back and forth which happens, which is unavoidable because there is a flip of velocities which happens. And you can see that also in the rudder chart, where the rudder goes from one side to the other side, indicating that we are having a flip of velocities when it takes a turn, just like here. So the vehicles actually come close to each other multiple times before they are able to avoid collision and walk away freely. And we wanted to compare that against the new APF method which we proposed, where we see that the collision avoidance is a little bit more smoother and the approach doesn't really require multiple interactions between the vehicles. So you can see here that when the vessel starts off, the faster vessel tries to overtake and the slower vessel keeps course until the faster vessel has actually crossed the slower vessel. Once this faster vessel has crossed the slower vessel does take a turn to try to avoid further potential collisions. So covering further, there is another COLREGS rule which covers the head-on situation, which specifies that when you have head-on situations, both vessels must try to take a starboard turn to pass each other. So the picture on the right here demonstrates the ability of agent 0 to do this, even when I have an agent 1, which does not follow COLREGS and simply keeps going straight. Again, when we look at the traditional potential, depending on where their goal location is, they can be on an imminent collision. And we already know that this is not the best approach to go forward for mobile obstacles. When we look at the velocity obstacle, it does seem to do much better, where they are able to take a turn. However, it does not follow COLREGS rule here by taking a turn to the port side rather than to the starboard side. However, it does avoid collision with a good margin of about 5 ship lengths between the vessels. The new APF which we have, since it is forced to follow COLREGS much better by forcing the vortex, which is going to make it turn in a starboard direction, we see that it does take a COLREGS following rule and tries to avoid the collision with the opposing vessel. And the margin of error is actually slightly larger than what we observed in the velocity obstacle field. And if you look at the rudder angle, there is no saturation which is actually happening here. So the rudder angle is much more controlled as compared to the traditional APF. So that advantage still remains. Finally, the third rule for navigation in COLREGS is when you have a crossing situation. When you have vessels which are crossing each other, then the one which is seeing the vessel come from the starboard side must give way and take a starboard turn to avoid crossing in front of the other vessel. And that's what you see on the picture on the right. Again, the green agent here with a yellow path is not following any COLREGS here. When we try to implement this with the traditional APF, we actually see that there is a deadlock which happens, which means they keep coming back and forth until they eventually collide. So, and the rudder actually does saturate quite a bit in this sort of a scenario. When we look at the velocity obstacle, they do much better. They are able to avoid collisions. But again, here it is taking a path which is not following COLREGS by taking where both the ships take a port side turn to try to avoid each other. However, the new APF, which is proposed in the study, is able to actually follow COLREGS very well. And because of the asymmetry due to the vortex approach, you see that the agent 1 is actually able to follow a fairly straight path with not much deviation, even when they are both interacting with each other. So the next question which we wanted to answer in this study was what happens when you have conflicting COLREG rules in operation? How does the vessel deal well with that? And we again wanted to compare between the new APF and the velocity obstacle approach. So the idea here is that we have three ships, Agent 0, which is going from 00 to 60,0, whereas the other two agents have twice the speed of Agent 0 and are trying to go further away. So Agent 0 and Agent 2 are on a head-on collision at 20,0, whereas Agent 0 and Agent 1 are experiencing a overtaking scenario. So with respect to Agent 0, there are conflicting rules here. So from COLREG's point of view, it must keep its course when it is being overtaken. But at the same time, when it's seeing a head-on collision, it must take a starboard turn. So we wanted to investigate whether it's able to actually get into the behavior where both of them can be balanced well. And we saw that, yes, it does take a turn to the starboard, but not as sharp as what you see from the other ship, indicating that the ability to follow COLREGs is somewhat embedded in it fairly well. So it does not violate the COLREGs strongly. Yes, it does take a turn to the starboard side to avoid the head-on collision, but it doesn't take a much larger starboard turn to confuse the overtaking vessel. Whereas the margin of error, if you see on the velocity obstacle side, it's much closer. The agent number 1 and agent number 0 are pretty close to each other at this point in the chart. So when we plot the distances between the agents, we actually can see that the safety margin is much larger for the new APF as compared to the velocity obstacle based method. We also wanted to investigate what happens when we have constricted waterways, and we implemented that too here, where the black lines here specify the banks which cannot be crossed, and hence we have a line source potential which is trying to push the vehicle away from it. In this case, we can see that obviously since the vehicles are being pushed away from the banks, they come much closer to each other as compared to when they had enough free space, but still they are able to avoid collision with each other and still follow COLREGs in somewhat of a constricted waterways. Finally, we wanted to test this entire setup in a more complex environment than what simply COLREGs specifies, because COLREGs primarily specifies interaction between two vessels only. But sometimes when you are dealing with busy ports like in Singapore or much of the busier ports like Mumbai, you will see that multiple vessels are actually encountering each other. So we wanted to test this in congested environments. So we tested them in 5 different congested environments. So the first environment has 1 static obstacle and 2 dynamic obstacles. The next environment has 2 static obstacles and 3 dynamic obstacles, so on and so forth, with the final one having 4 static obstacles and 9 dynamic agents all operating together. And that is the picture. The last one is what is the picture you see on the right. And we simulated such setups with a varied number of different starting points. So it is important to note that in this simulation setup, all the vessels are assumed to be of the same length, and the speed of all the vessels is assumed to be somewhere between the design speed of Agent 0 and half the design speed of Agent 0. So which means we are looking at a random distribution of speeds, and the goal is specified at least 50 ship lengths away from its starting location. All the vessels are started out with a random initial heading, and all the dynamic agents follow the same policy for avoiding collisions, which is the new artificial potential fields based approach, which is described in this study. So for each of these 5 different congested scenarios, 5,000 different simulations were conducted for each scenario, and a statistical analysis was performed to see how does the performance look. So some of the interesting parameters were in terms of computation time. How much time does it take to do a computation of what is the desired heading from each of these different methods? And we saw that the velocity obstacle, by definition, since it has to solve a velocity field and choose a velocity outside of this velocity field, is computationally far more expensive and takes more time compared to the other two APF-based methods. Obviously, the inverse square traditional APF takes much lower time because there is no computation required as compared to the second part, which specifically requires some computation of relative velocities of the craft. In terms of the mean time to reach the goal, we saw that both the APF-based methods performed somewhat similarly. Obviously, the velocity obstacle took much longer time because it doesn't want to apply rudder so frequently. So hence it deviates from the path significantly, and hence it takes more time to reach the goal. Something else which we wanted to check was what happens to the mean cross-track error, which means this is the mean value of the perpendicular distance away from the line joining the waypoints. And the velocity obstacle obviously has a larger value, whereas the proposed APF has somewhat of a slightly larger mean cross-track error compared to the inverse square law, but its control effort is much lesser. So the amount of rudder application is much lesser in the modified APF as compared to the traditional APF. Obviously, the velocity obstacle is expected to have the least control effort because it prefers to go in straight lines for most of the time. So the rudder is not being applied, and hence it leads to the lowest control effort, but it doesn't yield a much good result on the cross-track error. Finally, we wanted to see what is the success rate looking like. So we wanted to see if of the 5,000 simulations, how many percentage of the simulations agent 0, which is the main agent, was able to reach its goal effectively. And we were happy to see this result that with velocity obstacles in congested environments, it takes a toll on the effort and it takes a toll on the success percentage as well. The same happens with the traditional APF as well, but the new APF, which is trying to move the ship away from the obstacles using the vortex potential, seems to have a much better success percentage. But we still have about 2.5% to cover, which is definitely not something which the industry would accept as of now. But this is a good starting point in our belief that when we want to set up rules for COLREGS-based following, this serves as a good starting point. Once we performed these simulations, we were also interested in knowing where were the limitations of these methods and what was happening in them. And we looked up certain cases where failures were happening, especially for the velocity obstacle method. And we saw that why was a failure happening here? And we realized that at times, the velocities which it is choosing for both the agents flip back and forth. So it oscillates between two choices which are possible, and the agent is actually still stuck in this dead loop until the distance between the vessels really reduces and they are on a collision course. So you see that the rudder angle at this stage really flips back and forth multiple times, and the vehicle is actually not able to take a different path and continues on the same course and eventually collides. We did see that the 2.5% of the cases where the new proposed APF was not working, there too there were some limitations. Especially this limitation was happening when two vessels were encountering each other very close to one of the goal locations. So you see here that agent 0 is going to this goal, whereas agent number 3 is trying to reach a goal here. So when this agent is too close to the goal potential still has a considerable effect on it, and it tries to pull the vehicle closer to the goal and not follow the vortex potential as strongly. And this limitation does persist, and we have to figure out a better approach to actually get out of this limitation to cover that 2.5% of failure cases which we observe in the statistical runs. So in conclusion, when we look at it, we have looked at a harmonic function-based potential flows, and these are primarily based on sink potentials and vortex potentials, and they were primarily designed for COLREGS compliance. And it's important to understand that here we have assumed in this study that it is much more easier to actually apply a rudder than to change a speed for vehicles. Change of speed takes considerable time. So we assume in the study that the speed of the vehicle cannot be changed suddenly, and choosing a rudder angle is a better approach to actually avoid the obstacles. However, it does come with a caveat that when you really have vessels which are far away, you would want to kind of choose both rudder as well as propeller variations to actually avoid collisions in a better way. So that is something we hope to do in one of our future studies before we test into experiments. So these harmonic function-based potentials are able to handle both conflicting COLREG responsibilities as well as collision-free navigation in narrow channels. And the statistical analysis has shown us that it has a higher success rate and it's computationally much cheaper, results in a lower cross-track error as compared to velocity obstacle methods, and takes a lower time to reach the goal. And it is also moderate in the control effort that we need to apply. So it does look like that this approach is a good pivoting point for autonomous ships that aim to follow COLREG rules by construction. So the main idea here is this approach is very interpretable in the sense that we are not using any deep learning models here, and the rules are very interpretable in terms of we can exactly know why certain decisions are being taken and how they are affecting the craft, rather than when we look at deep reinforcement learning based approaches where the interpretability becomes a big issue. Both methods have their own advantages and disadvantages. So this was our talk on more of COLREG-based compliance using traditional approaches using artificial potential fields. So thank you very much for the opportunity. So if you want to know more about our lab, you can definitely look up our website or follow us on LinkedIn, or you can drop us an email at any of these email addresses, and we'll be happy to respond back. Thank you very much. I give the floor back to the session chair, Mr. Srinivas. If there are any questions, I'm happy to take them now.
Thank you, Dr. Abhilash. That was an excellent presentation and very good insight you have given us on a lot of new topics. Before we conclude, I would like to, we have got good number of questions. I think you are able to see the QA box, Doctor?
Yes, okay, some of
So
them.
we can take the first one from Mr. Kapil Kekre.
I see one from Professor Krishnan Kuti, but I didn't see the one from Mr. Kapil that you're talking about.
He says, thanks for the opportunity. Congratulations to Dr.
So Dr. Abhilash, so the ones which Mr. Srinivas is referring is the Q&A box, and we also received some question in the chat box as well. So that also we can take, but I think some.
Okay, all right, okay. I see the Q&A box now.
Yeah,
Okay, all right.
and maybe Dr. Ang, if you want to add, so generally we can also have the chief case address, and then we can have the Q&A session, or we can continue with this, and then like both ways is fine. Mr. Srinivas. Yeah.
I think that sounds a good idea. We can have an address from Dr. Captain Jayakumar, sir.
Yeah, I think that would be good actually, and we can come back to the questions so that people have some time to write down more questions also.
Correct.
Thank you, Mr. Srinivas. At the outset, I must thank the Institution of Naval Architects for inviting me to this session. And I must say, a very, very brilliant presentation by Dr. Abhilash. So it is really a fantastic presentation. I was seeing some of the responses also. It was very good. And before I give my views on this, I would like to, as I said, not only thank the Institution of Naval Architects, but special thanks to Mr. Iyengar and Mr. Dasgupta Sahab. He was here some time back. I don't see him there, but thank you all for having invited me. With regard to what has been presented, I have a few points that I was, when I was reading up about it, And I find that one of the questions that have been raised is something akin to what is there in my mind. As a navigator, normally what we do out at sea, the first thing what we do is we would rather take a action well in advance rather than wait for the situation to develop into a close quarter situation. So supposing I see a ship maybe 8 miles, 10 miles from me on the horizon, and then I see that there is a possibility of a collision in due course, we would assess it is whose responsibility to keep clear. The giveaway vessel normally would take action well in advance so that there is no possibility of a close quarter situation arising. So I suppose your experiments may need to factor in those, because if you consider 15 ship lengths, I'm sure a lot of the seafarers, the navigators would be having stress issues on that, because that would be pretty, we would call them as close quarter situations. Again, factoring on a ship, what happens generally is we can have a course that we are steering. Let's say we are steering north, 000, but the winds and currents could actually make our path a little different from what we are steering. May not be a little, it could be substantial many a times. It could be that I am pushed substantially away from the northerly course I am doing. Maybe I am going slightly on, depending upon the direction of the current and the swell and the wind. I may be making 5 to 10 degrees sometimes as compensation to counteract this. Obviously, they would need to factor in these aspects also. The third one that I found is that especially when I link it with my experience with the autopilot that we have, on calm weather conditions, we find that the track, when we keep the ship to maintain a particular track, it is reasonably able to maintain. But when the weather gets rough, the command that goes to the module is to keep moving the rudder substantially, which puts in a lot of stress. So we then end up adjusting it to make it that you don't have to respond. The course that we are saying is not so sacrosanct, especially in the mid-ocean, that if you are a couple of miles here or there, it really doesn't matter. So these are some of the practical aspects that I think the technology that is coming in will need to look at. Again, there are different maneuverabilities in deep waters, in shallow waters, in currents, and high maneuverable vessels, low maneuverable vessels, high-speed vessels, low-speed vessels. Of course, these are complexities that are there, but nothing that technology can't overcome. And today we are moving on to a stage where, whether we like it or not, automation is going to happen. And it is going to happen much faster than most of us can envision. So that what we will see happening is, in the initial stages, you would have autonomous or semi-autonomous vessels with manned vessels. And over a period of time, there will be maybe substantial years down the line when it becomes fully autonomous all the way around. So the technology that we are now looking at is actually what is the precursor to what would be the final product in the years to come. So I must appreciate the research that is being done by Dr. Abhilash and his team. Congratulations. And once again, thank you, Institution of Naval Architects, for having invited me to say a few words. And thanks, Mr. Srinivas. Thank you all once again for the patient hearing.
Thank you, sir. I think that was a very good input from the practical point of view with all the experiences what you have, and that really, I think definitely, I think it will help in the further research and the further experiments which Dr. Abhilash and his team would be taking up. Dr. Abhilash, please.
Thank you, Captain Jayakumar. It was, you're definitely right that we are just scraping the surface just now. There are a lot more things which we need to go put into it. And as you mentioned, some of them are, the maneuvering really changes when you enter shallow waters. It's no longer the same as what you presume in deep waters. And similarly, the speed reduction has not been considered here, which is a vital aspect of when you actually want to do a collision avoidance. Something which also is coming up, as you rightly pointed out, that the industry is kind of slowly going to first go to probably remotely operated vessels first and stay there for a long period of time because of the requirement of who has the onus on different aspects. Regulatory frameworks have to be fixed up. So there are quite a bit of things before we actually see a reality of completely autonomous ship operating in the open ocean. And coming back to the idea which you did mention that when we are out in the open ocean, yes, we may not care so much about the course, even if I'm maybe a few hundreds of meters away, but all still on the same course really may not make much difference. And that's true. The idea here was to see that when we are operating in a more congested environment, something like a Strait of Singapore or something like these areas where congestion is quite strong, whether can we do something better than what is existing out there. But absolutely, I take your point that this is just the surface and a lot more needs to go into it. Actually, I was definitely looking for some good industry help too. And possibly if you can connect me with the right people, I'd like to talk to more ship captains and masters and see how this sort of an exercise can be, or what can we learn from them, which we can leverage in formulating better rules for these sort of systems. Thank you a lot for the suggestions.
Thank you. I think definitely, Captain Jayakumar, I think we'll have a few inputs, contacts which can be helpful to you in the study further. And as you said about remote control, that may be the real immediate reality, but it has got its own challenges because of regulatory requirements and also on the getting the actual situational awareness at the remote center, sensor fusion and all that has got on. Okay, I think we will take the questions from the QA box.
Yeah. Okay. I think I can see this one. Okay. Presuming this is a question from Mr. Kapil Kekre. Presuming a faultless collision avoidance system is designed, considering COLREGS 72, how do you see dealing with the challenges of the changes envisaged in COLREGS 72 and exercise under progress? Yes, that is true, because right now the IMO is trying to figure out how to bring in the autonomous vessels. I mean, a few years back, there was no definition of an autonomous vessel for IMO. I think almost since 2016 or 18, I don't remember the year. It's only then that an autonomous vessel was really formulated into the picture. So we'll have to see what exactly are the changes and what regulations come into the picture, and how do you deal with the idea that when the other person is not dealing with COLREGS, or the other person is not following COLREGS, and when the other person is not following COLREGS versus they are manned, when the other person is not following COLREGS versus they are autonomous. What are the difference in rules which will be specified and which will come up? We will have to definitely adhere to that. Probably, yes, that exercise under process needs to be complete before probably we can see a good amount of answer in a certainty in that direction.
I think Mr. Kapil, if is there, I think you have answered his question. Can we move the next question, please?
Yes, thank you, sir. Thank you. Thanks. That answers the question.
Thank you. Thank you. Thank you for the question. And I think that was a way forward. And the next question from Mr. Kamal Pal, sir.
Mr. Kamal Palit. Okay. How do you take care of ship side current or wind, or when wave or hit ship side at right angles? Yes, thank you for that question. So, what we did not show here was the effect of wind and waves, but we do actually model these in our simulation program. We do take into account what is the frontal projected area and the lateral projected area and the wind coefficients when they are available. And they can be included into our simulation module to understand how well we can deal with them. Typically what happens is this is more of a control problem. So when we have a current or a strong wind, the integrator part of the controller really takes care of this without us having to worry so much about it. So which means that eventually when I have a strong current which is trying to push me away from the line joining the waypoints, I do move with a side slip angle or with a rudder in place so that I can actually slip off and go still in the same direction. So, but as Captain Jayakumar pointed out, at times that can lead to trouble when the integrator gains are not tuned correctly. You can see large oscillations come into the picture. And at that time, obviously, a human is required. But if you do the tuning a little better, there are ways to get past it. The other way to get past these problems is to go for nonlinear controllers, uh, which involve being able to cater to different speeds and different dynamics and robustness in controllers. And that's a big area in how do you design robust controllers. And that usually does take care of some part of what you are asking.
Thank you. I think then the next question takes care of you answered the first one, which says that then the purpose of installing radars will be lost. I think since you're already taking care in your calculations, engineering calculations, I think that is clear.
I believe that there still might be some use of the radars, particularly to not just for the weather purposes, but to also to look at what is for weather routing. And that's another area which we have not considered in this analysis anywhere. So I can see a good reason for the radars to still be there. But obviously, you can also have it for detecting larger vessels far away, and that does work to some extent.
And before we go to the next question, can I have just one small dot because from what you said regarding taking a person taking over? Does it system give an alarm kind of thing, or how does the taking over happens? Is it
Yes, so that is not something which we investigated in this study. You are right that when does it actually sound the alarm and take over? That is quite a challenging behavior. But usually, what we would presume is certain thresholds where when you are getting within certain distances of your obstacle and you still see a collision risk being there. So it would require quantification of what is called as collision risk index. Now there are different ways to do that, and there is no agreed upon literature as far as I know. There are different people come up with different methodologies, but the standard consensus so far seems to be to use what is called as distance to closest point of approach, which means that given that I have the current velocities and the current trajectories being maintained, what will be the minimum distance between me and the obstacle as I pass through it? That serves as so most of the collision risks indexes that I have seen seem to leverage upon it to figure out what is the risk index. Now, whether that is the best way to go about it, I still can't comment on that. Probably some more research needs to be done on that, but that's at least a good starting point.
Thank you. We will take up the next question, the first clear box, that is from Mr. Deepankar Das.
Yes, why speed reduction is not being considered in the algorithms? I noted only course alterations in the simulations. Yes, indeed. Here the idea was to kind of work off in a little congested area. If you see, most of our simulations were about in 100 ship lengths cross 100 ship lengths, which is far more constricted than what you would see out in the open ocean. And when you are far away, the speed changes are much more faster to be done. But when you are in a constricted environment, the speed change does take considerable distance to be traveled upon. So the main goal here was to see what best can be done with course corrections particularly. But as I said, mentioned in the presentation too, we do need to consider speed changes in a future version of this. That's definitely on the books.
I think Mr. Deepak has does. It has, sir, your question is well answered, I believe.
Yes, yes. Thank you, Doctor. Understand.
Thank you. And we'll take up the next question from Mr. Bilbadal Sarkar.
Okay, I think the next question also seems to be on a similar lines, saying that in congested water, speed control must also be considered, keeping in mind the availability of sea room. Do you think that control of propeller along with rudder should be considered? Yes, I definitely do think that the control of propeller along with rudder should be considered, particularly for ships which are under-actuated. Running the propeller faster will definitely increase the flow over the rudder, which allows it for having a little better maneuvering capability. And that is something which we definitely did not leverage on in this particular study. So that is something definitely worthwhile looking, especially when you have low sea room availability. That does definitely make sense.
Mr. Sarkar, I think.
Yes, yeah, I think it is the question on the similar line of Mr. Das as well. And control of propeller, meaning that speed reduction or speed variation. Thank you very much.
Thank you, sir. I think here we have finished the questions clear, but there are a couple of points in the chat box.
Yes.
Very rightly, people have appreciated your presentation. That is one of the two topics. And one comment from Mr. Krishnan Kuti.
Yes, what I'm wondering about the possibility of collisions when you consider the vast area available for vessels to change course, the comparatively slow speed at which vessels are moving compared to the road vehicles, with the only disadvantage being the momentum of the vessels. Add to this the capabilities of modern machinery and equipments. When you consider all these facts, the chances of collision should be very, very remote. But the facts are different. Okay, why? Okay, I am not fully sure I understand the question fully.
May I request Mr. Krishnan Kuti to elaborate?
Yeah. Can I clarify that?
Yes, sir.
See, the ship speed compared to road vehicles and all is very small. A lot of space is available. It's not so, I know when you are in channels and different otherwise, but if you look at the collisions, history of the collisions, many of them could have been avoided if you consider all these facts. But what is the real reason for not being able to do that? Why collisions take place in open seas? Is it because of human error or machinery?
Usually my understanding, or maybe obviously the people in the practical industry can give you a probably better answer to that. I'll probably ask some help from Professor Captain Jayakumar in a little bit. But my thought process is that many a times it comes down to the human factor. It's a decision which is taken at the human level, or a decision which is not taken at the human level, usually is somehow responsible for the eventual action which results out there. So it's not necessary that what you call the ideas which we are discussing here are foolproof or soundproof, but it has to be taken with a pinch of salt that whenever a human is in the picture, fatigue and other things do come into the picture, and these are things which are not really accounted for when we are talking about collisions. Most collisions, to my knowledge, can be, at least in the studies that I have seen, almost 80% of the collisions out there, accident reports, can be attributed in some way to the human's decision or human action at some level or the other. Captain Jayakumar, would you like to add something to that?
Yes, I will. Collisions at sea, especially in open areas where there is no restriction of space or depth, can occur only because deviation from the rules of the road. Why did the deviation occur? Was it due to human error? Was it due to any machinery fault? Or was it due to unexplained thing? Would depend upon the circumstances of each case. But by and large, in open sea, it is not very easy. As I said, I would, when I was sailing, or I know when I was my seniors, and I'm sure most of my juniors also, you see a ship far off, you decide whether it is your duty to keep clear or it is the other vessel's duty to keep clear. If it is your duty to keep clear, you may as well keep clear well in advance, where you just need to alter a few degrees of course, and you can keep clear of her. As you come closer, you have to give sharper course alterations, and that will deviate you substantial from the course you are steering. It will inconvenience most of your crew, just in case the weather is bad and you are having your large alteration brings in changes in the motion of the ship. So as long as you are the giveaway vessel and you have not taken action in advance, there is a possibility that once you come closer, then it becomes more difficult. When the other vessel is supposed to give way, that is the time when there is a doubt whether should I take, because the rule always also gives you an opportunity. Even though the other vessel is to take action, you can also take. So you will find right now what Dr. Abhilash has done is a straightforward, conditions that have been interpreted in the ROR, but you could find a million possible variations to that, where a ship could be considered overtaking even when it is coming at an angle. So each situation has its own uniqueness, and it is the skill of the navigator and the machinery that is there to see whether it does not result in a collision. And most probably in the open seas, you hardly hear about collisions that occur.
Thank you.
Thank you, sir. And Captain Jayakumar, sir, I have just one small dot more than to Dr. Abhilash. Now the new IMO, the draft code is also coming up on this mass and all. It says that the vessel can be different autonomy modes in the throughout the journey. And in all the probabilities, the present work and practical implications will be more on the high seas keeping the vessel. So in the close harbor quarters, I think still it will be manual.
I think, see, what we are looking at is a stage where currently IMO is coming up. See, in the Norwegian waters, they've already tested where close to the coast, vessels have moved autonomous without this thing, of course, closely monitored. So you may call it autonomous. I would call it totally monitored, wherein it is a test taking place. It is not as if there is no one monitoring it. And it is considered successful. But there are no regulations in place. Today, if a totally autonomous vessel is supposed to be coming into an area which is not yet ready for it. Today, a ship is supposed to maintain a proper lookout by sight and hearing. Now, if it goes to a country's waters, which does not yet, and since there is no international regulations yet in place, how would that country accept that? So these are issues that are there, which IMO is currently in the process of deliberating and coming up with a draft voluntary code initially. And once that is done, they will run it on a trial run, see what are the difficulties in having that, And then would come the mandatory autonomous code. Even then you will find today there are a number of ships that are there. It would be very easy to say that we overnight change all of that. But it doesn't happen that way in real life because it's a huge investment. And if there is already so much investment sunk in the current ships that are there, I am not talking of the very old ones, it will take a few years before it slowly starts getting phased out. It will, of course, happen that over a period of time, when the number of especially after the mass code has come in and number of countries have started implementing, number of companies have introduced this, then slowly you will find that the manned human interference directly from the vessel will slowly start getting phased out. But my estimation is it will take some time.
Okay, sir. I think as you rightly said, it will be progressing at some steady pace, and humans are still on board. It will be quite some time before the people are totally removed from the ship. That will be quite a far off scenarios.
Yeah.
So, the autonomous system or technology is definitely going to help the people in doing a better navigation and avoid accidents.
Yeah.
May I, this has given me another, why, considering all that expenses, additional expenses required to make a vessel autonomous, you are saving what? The wages, right? Crew wages only. Is there a, so do you think it is worthwhile to make autonomous ships and thereby, making few jobless?
I think, Mr. Kuti, my personal view on this is technology cannot be stopped. Whether we like it or not, we have to face the reality that technology will keep moving. If you would ask the seafarer 30 years before whether he could manage without a radio officer, we would say no. But technology came in, it moved on. As far as what we need to always remember is the ship is not made for the seafarer, or a shipping company does not buy a ship for the seafarer. It is for the company to make a profit and for optimizing the profit and moving the goods in the most efficient way. If a more efficient way comes in, and if it is going to result in certain loss of employment opportunities, that is the sad reality. As long as it is efficient and cost effective. If it is not efficient and cost effective, it gets discarded. It won't come in as a technology. Because if I am an investor putting in millions of dollars to buy a ship, I am not going to risk it just to say that save one seafarer's job. It is not that. It is, if it is a proven technology wherein it is going to save that industry a substantial amount to transition to the new scheme, then you will have takers. And it will again be slow and steady. It will not happen that overnight what I have invested in, I would want to close it down and then go and invest again into a new venture. So that is why you will find when you look at the IMO interactions and the mass code, you find the dates that you are seeing. It is a reasonable number of dates. It's giving time to the industry to prepare itself. And yes, technology demonstrations are being done. Like Dr. Abhilash has done his study on in a contained environment. Similarly, in a larger environment, it has been done. And slowly it will progress. So there is no way that we can close the technological progress. That's my view.
Yeah.
I can add a little bit to that, if I may.
Yeah.
So the other thing which I would like to add to what Captain Jayakumar did say, and I quite well agree with him on most of the aspects, is that when we look at this, the primary idea will be the finance which will drive the thing. It's the economics which will drive the technology for it. And the reason why the economics works out in this favor is not because of the amount which is paid to the seafarers. That's actually a drop in the bucket compared to the size of the business. In fact, if you have an unmanned vessel, you can do much more things. For example, you could even change the design of the vessel altogether because there is no crew on board. And you could actually make it much more effective in facing a wind resistance or minimizing the wind resistance or minimizing the requirement for underwater resistance and other things like that, which might make it uncomfortable for the crew at times and which are not being done as of now, can be adopted when you want to move for such models. And definitely one other major aspect which they will look at is the amount of risk which they have with accidents possibly happening due to the human in the loop versus when they do not have the human in the loop and go completely autonomous. If the savings really work out in the favor of that, that's when you'll see the autonomous technology really come into the picture completely. Until that time, it will be a slow stepping process, one after the other. It's not going to happen all of a sudden. So definitely companies will be interested in testing the waters to see whether it holds a potential savings for them in the long run. And that's how I see it.
Yeah, it's true that when you remove the human being from the ship, the owners have got a lot of freedom to, to take decisions based on their profits or things like that. Because the most difficult thing is to accept loss of life. So if you can avoid that, I know that is, and not only that, all these things are done after doing a lot of study and all. My thing mentioning about the seafarer was not because of any sympathy for seafarer or anything like that, but what you're saving by removing the crew from the ship. I was wondering whether it is worthwhile and comparable to the extra expenses you have to extra money you have to spend on making on an autonomous vessel. That's all.
I will just add,
technology cannot be stopped.
No, I will just add one point. Most of us may not be keeping track is that amongst the expenses of a ship, running expenses, 30%, if you put it in a general scale, 30% is on manning, 30% is on bunkers, 30% is on maintenance. If you generally look at it. So if you are looking at it, you are looking at a substantial saving of 30%, which is something that gives an incentive to the ship owner to experiment on. Add to that, when the human being is not there on board, the safety factors can change, not just the design, like you don't need a lifeboat because there is no one on board. So a number of requirements can change. So these are factors that will make a play, and let's see how it progresses.
Thank you, sir. I think, as you rightly said, it takes time, and the first step could be, before going totally autonomous, maybe a minimum crew on a bridge like we have in engine room. So maybe a periodical unmanned bridge. That could be a one step forward before we totally take the people off the board. And anyway, as per the new IMO code, I think scenario is shifting from bridge to ROC. So jobs are still there.
They are just different jobs.
Are there any further questions in the chat box? Or
I think there is one question: inland navigation capabilities for APF. Please throw some light. Okay, yeah. So when we talk about inland navigation, it does come with its own challenges. And I did kind of show a very simplistic example. That's not quite how simple it will be when we want to navigate the inland navigation channels. And if there are stronger currents, like upstream of the Ganges, you also probably will need some different types of rules for different side operations. If you're going against the current versus if you want to go along the current, there'll be different rules needs to be probably be formulated. I've particularly not yet thought about it. It's an interesting idea to probably think about how APF can be modified for such scenarios. Okay, I think the last one looks more like a comment.
I think let's try to sum up.
I think it's more of a summary of what all we have discussed so far.
Discussed and what the mass in general has the positive and challenges, you could say. One thing.
Yeah.
The Q&A box, there's one more question which can probably look at.
Q&A has one more. Okay. Autonomous vessels plying in the Baltic region and so on are controlled by a shore assistance with a minimum manning of 2 to 3 people on board, which means that the connection between the ship and shore must be fully encrypted. All right. Since APF model is incorporated in maneuvering systems, how do APF model and maneuvering systems ensure they cannot be hijacked or hacked? Okay. All right. So this is more of a question on cyber security of the things. So I believe that the APF cannot necessarily make it sure that it cannot be hacked or hijacked, but it's more of a cyber security problem which we need to address there, or cyber physical systems where we need to address there. Typically, from what I understand is you have redundancies in place, and redundancies are usually in place which are utilizing different types of mechanisms to figure out where the vessel is and what the vessel is doing. And if there is no corroboration between multiple different types of sensors which are on board the vessel, usually it's a red flag for the operator to think about something is not right. And that's the main idea if you look at something like GPS spoofing and things like that, where they are trying to fool the system around. The idea is to see, do I have a redundant mechanism in which I can measure things, which could possibly tell me to or give me an idea that that's not really the situation which I'm seeing from the other sensor. So I probably don't have the full knowledge to answer that question completely on cyber physical systems. That would be someone with strong background on encryption and other things who can probably give that better answer to that. Sorry.
Maybe I can just add a couple of points on that. The earlier the ship systems was depending mostly on the encryption and the security on the communications with VSAT providers, satellite providers. Now recently, IAX has come out with requirements on cybersecurity. WhatsApp audio. Cybersecurity, where they have about 30 requirements in the ship, and about 10 additional requirements when the ship is communicating from ship to shore, which starts from encryption, how to giving a permission to remote logins, and whole lot. I think that the new requirements have come from IAX and which have been implemented in all the class societies. And from 1st of July, they are going to be implemented, which will address these issues with encryption and even remote connectivity. Of course, there are the minimum requirements, but as we go along with autonomous ships with remote connectivity, there are higher levels of controls are available, which can be enforced upon. So there is a nice standard called 62443. It has got 4 levels of security levels. One can go for the highest level to ensure that your systems are secured when you're transporting outside. Thank you.
Just to add to this, when it comes to encryption, one thing of interest was particularly in modeling is the time to encrypt and the time to communicate, particularly when you have a remote system, which means the time lag between the response and this thing, which was generally we take only the rudder response, the propeller response. Now we have to add the communication time response also into our model. I mean, that may be a factor or that may not be a factor. That will be known only depending on the time to encrypt, the time to decrypt, and the time to for this thing, particularly for remote sectors. This may not be applicable when we do a bridge-based control, but it may be applicable when you do a remote-based control.
Very true, because there are certain calculators available, because not only the encryption, because depending on the communication media what you're using, like satellite time and the time to transmit from, suppose you want to give a command to rudder, it starts from your remote control center and you have a kind of time lag in the RCC, you have a time lag in the communication network. Again, on the ship, finally rudder mechanical time lag. Add to that, you have the encryption also. So the total time lag should not be determined to the safety algorithm. It again depends on the envelope, what you say, allowed which you can operate freely. I think that decides a boundary of the ship, which is typically in the autonomous vessels you call operating design domain. So that depends based on your sluggishness of the vessel and the time lag. We decide what is the safe area, a safe bubble around the vessel, which can be allowed to go free in the ship.
Okay, I don't think I can add anything further to that.
I think most of the questions and chat boxes are over.
Okay, I think we have I think audience were very interested in the presentation, the excellent presentation, because we start 1.5 hours. I think we are nearly more than 2 hours now, nearly 2 hours. I think that was a quite interesting presentation. We had a good interaction from the speakers and good inputs from Captain Jayakumar, sir. I think we have started with the activities at your lab, what the autonomous lab is doing, and the conventional methods of controlling the ship trajectory and pathways, and the use of APFs and advanced new APFs, and how it is resulting in a better control, smoother control with less stress on the rudder. Thank you, Sir Doctor. I think we are at least we have some takeaways now. We have learned something new, which is most critical, but at least we know how the dynamics behind the maneuvering, at least if not the equations part of it, at least it is given a clear insight how things are going on. And it's a quite challenge, and really thank you to, and you and best of luck to you and team. With if it's okay, we can conclude the session, and I hand over to you, Mr. Ankar.
Thank you, sir. It's been a very interesting session with a very good audience participation also. Concluding, and I'll begin my concluding session with first thanks to our chief guest, Captain Jayakumar. Sometimes I actually request quite late in the day, sort of Wednesday, Thursday, and it's indeed, I'm very happy that you could just join, even though it was quite late in the day. And similar thing to Dr. Srinivas. I mean, even though I know Mr. Srinivas in several conferences, he also readily agreed to chair the session, and I know his expertise in the field. And of course, Dr. Abhilash for his excellent lecture. The session was very good, and today we had 37 people who had joined other than whoever is in the panel. It was quite a good audience of 37 people had listened to the lecture, and we saw questions. Around 5 or 6 people had actually participated in questioning also. So thanks to all the people who participated by asking questions, as well as 37 people who joined the lecture. And in the background, now INA is going through a transition where Dr. Manu Kurla has taken over as the president of INA. He has also joined the lecture today. And our earlier president, Mr. Dasgupta, also joined today's lecture. And both of them, this being a transition state, both of them guided us in the background for this to happen. And Mr. Amir Ahmed, who is the professional secretary, was actually hosting it completely behind, so that we are having this seamless internet webinar with all this technical support behind, which Mr. Amir is doing, and the INA office which is doing. Thanks to them also. And thanks all, and have a great evening.
Thank you, and thanks for the invitation.
Thanks.
Thank you. Thank you very much.
Thanks.